So today we're on the last chapter and talking about behavior types and behaviors. And here are some pictures of morphisms or of diagrams in a hypergraph category that Brendan talked about last time, where the wires, say, are various types, and the boxes here are kind of morphisms that that go between types. And so we have, say, a sensor, a controller, and a motor sending each other information. We have inside of a sensor, we open it up, and we see there's actually two sensors and a processor, and they're all behaving in some way. But the question is, what is behavior? So maybe I'll let you just think about for a minute. When you say that these things are doing behavior and they have certain behavior, what is it that you're talking about? Just maybe think about that with someone, just for a minute, or just by yourself.
I always think they're resistant constraints.
Yes, I think having behavior.
Or what are you doing right now? You're behaving. You should also be one of these boxes.
Super heavy, like operational semantics, which is like that's not how they I think it's I only learned about this how behavior is justified.
Okay, so any ideas? What can you say about behavior? What kind of thing is it? Yeah.
From sensor inputs to motor-driven outputs.
Okay. Instantaneous or?
No, certainly not instantaneous.
Changes over time?
But
Yeah, so
the inputs change over time.
the inputs are changing over time?
The map can change over time too. But
the map might be changing over time?
I don't see a neural net there, so probably not.
The output of the sensor may be based on things that came to the sensor a millisecond before. The controller might be taking into account things that happened 10 minutes before. Who knows what, or the processor might be taking things into account. When you look at my behavior, you can tell that I'm not, at least from the outside, whether it's whatever's happening internally, outside you can tell that things that happened 5 minutes ago are still affecting what I'm saying now. So if you look at the kinds of possible things I could do, so what I want to say a behavior type is, or a behavior, is that it's a set of possibilities that you can name. So what are the possibilities for a bicycle behavior? Well, you could say it has a wheel speed, it has a pedal speed, it has various speeds, I guess, and gear ratios. And you know that the pedal speed times a ratio is less than or equal to the back wheel speed. And when you do that and you say, I know that's true, then you're restricting the possibilities of that behavior type. To say a bicycle is the kind of thing with this sort of behavior. And I am the sort of thing, when I'm giving a class, that has a certain kind of behavior. I don't just do any of the possible things I can do. I do some of them. And so that's what I mean by behavior type. All the things I'm capable of doing when I'm doing David, I guess. And a behavior is one of those. Just for terminology, yeah.
So from the viewpoint of cutting out possibilities,
yeah.
If we want to embed this in time and have like actual millisecond delays, shouldn't there be a small feedback loop in the processor to itself?
The processor will be something whose job it is to manage the relationship between what's happening on its ports. So you take what's happening on all my ports, whether they're motor ports or sensor ports, and I'm managing a relationship between all that stuff. And I'm allowed to do it with anything inside of me that is there. There could be a feedback loop inside, because I can open this thing up and see all sorts of crazy stuff going on. Yes?
Would you say that the behavior type is a set of possibilities with a constraint?
Yeah, it's a set of possibilities changing in time. And if you say that you want to cut out from all of its ports, say, those that satisfy a certain relationship, then that would be the constraint. So out of all of the wheel, pedal speeds of a bicycle, only certain ones satisfy that the bicycle is intact. Okay, so that's what we mean by behavior type, a bunch of possibilities parameterized by intervals of time. Because if you take all the things I'm capable of doing, it's not in a microsecond, it's over intervals of time. So that's the way I want to look at behavior types. And the way I'm looking at it when I say that is that there's a certain topos where whenever I talk about a type, it'll be called a behavior type because I call it the behavior type topos. And so whenever I talk about a type in this topos, instead of a type like the natural numbers or the booleans, the types in this topos will be behavior types. So any object in this category, a topos is a kind of category, and any object in this category will be a type of behavior. And any morphism in this category will be a way of taking types of behavior type A and turning them into types of behavior type B. So that's what this class is about. These are pictures of relations in a topos, and you can form relations in any topos, and they form a hypergraph category, which makes these diagrams legitimate, because Brendan talked about relations, or the hypergraph categories last time. But these are talking about behavior types and relationships between them. Okay, so the idea is we're going to be thinking, I mean, if we want to go into that topos, I could create a topos and you could too. And anyone who wants to can create a topos if they know how. And once you do, it makes it so that any statement you make, any mathematical statement you make, you can interpret it in that topos, and it will mean something relative to that topos. So let's say I have a group, then if I interpret it in the temporal topos, that will be a group changing in time. If I say I have a ring, it's a ring changing in time. I could say it's not changing. I could make an axiom about my ring that says this ring is always R. Or I could say this is a ring that is allowed to change in time. In here, just in the same way, a motor is a type of thing that is allowed to change its behavior through time. Its type of behavior remains the same, but it changes through time. So a topos is a mathematical world. It's a world where mathematical statements can be interpreted. Like I have a group. If I have a topos for a topological space, that group changes through the space, is allowed to change through the space. So the most common topos is the topos of sets. And that's what we'll be talking about today. So all this high-level stuff we're talking about today, that I started with, kind of the motivation, was worked out in a project I did with NASA and Honeywell a few years ago, where we kind of wrote out a topos where the kinds of things I was saying here make sense. So a certain notion of time, very like standard notion of time, not relativistic, just kind of what you think of as clocks, where we discussed how this would all work. But today I'm going to talk, and tomorrow Brendan will talk about kind of general toposes and the kinds of things you can do in them, how you can make logical statements in any topos, and they get kind of unfolded into statements about things changing in time or changing through space or whatever. The most common topos that you've already heard of is the topos of sets. And so a lot of the structure that holds in the category of sets, which is what we'll talk about today, is true in any topos. And if there's a topos for time and a topos for space and stuff, what is this one for? This is a topos. What's it for? It turns out it's the topos corresponding to a single point. So if you have, if instead of a big topological space like a sphere, like all the things that can happen on the surface of the Earth, or a big topological space like time, some kind of intervals of time, all the things that can change through time, this is the stuff that happens at one point in space and time. And the way that's reflected in the logic is that when people say statements like a proposition P, like 4 is even, that's true for all time. It's not a timeful thing, and it's not a spaceful thing. You don't check whether 4 is even on Wednesday or 4 is even in Africa. 4 is just even. Whereas it's raining, like in logic textbooks, they like to say, oh, we can ask P is any predicate, like P is it's raining. But that's not good, because that's not true, either true or false. So in set theory, for example, we have the statement P or not P. For any proposition, people might write P colon prop. You could assume that P or not P holds. But that's saying that something's either always true or never true. 4 is either even or it's not. Whereas it's raining is true here on the Earth and there on the Earth, on Wednesday and not Thursday. And so that's when we talk about set theory, which is what we always do. We're talking about things that are always true. And the point is that anything we'll talk about in the temporal topos can kind of change through time. And a truth value is not just true or false, but when is it true or where is it true? It's true in Detroit and Africa and here and there and this time and that place. So those are what are called truth values. And every topos has a notion of truth value, and they're much more expressive than they are in the topos of sets. They're like, where is it true? When is it true? Any questions about that? It's kind of a high-level idea, but that's the topos theory is like a whole. I mean, it's a way of thinking that's kind of I don't know, makes me happy. It's like a very it's like a jewel of mathematics to me. I think it's yeah. So I hope you enjoyed. I hope you look into it and think about it. So today we'll talk about the topos of sets, and which is the topos of a single point. So a lot of things are very simple, but they generalize. So everything I'll say today generalizes to an arbitrary topos. This is one thing that doesn't generalize to an arbitrary topos. This is an extra axiom you could add in a proof assistant like Coq and say, I assert that for all p, either p or not p, and you've really limited the expressivity of what you're working on. But it gives you a lot of proof power. So, yeah.
Does it make sense to think of topos as truth statements, whose truth or untruth depends on like value from a text? So if it's times like a real value.
Yeah. So in a topos, you have something that classifies all your truth values. And that thing could be called prop if you're used to thinking in terms of proof assistance, or it could be called omega if you're coming from pure math. That's just what chief theorists or topos theorists might call it most by default. The topos is not just prop. It's the world where prop is one part. So we'll talk about that. Okay, so if you want to like have everything I say happen twice, you could take everything I say about sets and replace it with the category of graphs. Graph, you've seen before, it's a functor from this category to set. Or you could fix any categories here, any kind of database schema, and look at all the functors from that thing to set, and you're going to get a topos. And everything I talk about, you could say, what are limits and colimits of graphs, or what are limits and colimits of a database instances, or what is the subobject classifier in the category of graphs, or what is the subobject classifier in the category of database instances for a certain schema. So if you want to take everything I'm saying about set and you find it boring and you already knew all this, then just go up a level and pick an arbitrary topos like the topos of graphs and think there. What are the exponential objects in the topos of graphs? So what I'm going to talk about is some properties and structures. In arbitrary toposes, except only sets. So I don't know how to say that right, but I'll pretend I'm saying sets, but if you already know something about toposes, or you want to, just take any time I say the word set and think object in a topos. Okay, so what are true in any topos? So limits and colimits exist. All limits and colimits exist. So for example, you have a terminal object, an object that receives a map from everything else. Sorry, a topos is a category. Remember, a category has objects and morphisms. It's a category with some properties, and you can define a topos in various ways. But here are some properties of it. So it has all limits and colimits. It has a terminal object, which means there's some object in that topos that everyone has a unique map to. It has products. So for any two objects, there's a product, or any finite or infinite number of objects, there is a product of all of them. And it has pullbacks. What does that mean? If I have three objects in the topos, for all diagrams like this, there exists a diagram like this. That is a pullback in the way we talked about last time. Every diagram has a pullback. There's an initial object. So toposes are categories with lots of nice properties. They have a terminal object, they have an initial object, they have products, they have coproducts, they have pushouts. have all this structure in them. Not every category has that. For example, the category of manifolds doesn't have all pullbacks or all pushouts. Yeah.
That's because we have all limits and co-limits.
Yes, and
so
these
it's
are the
like
ones-
You can
this
take
is-
any diagram over there and those correspond
For
to
any
the
diagram shape I, there is a
Yeah.
limit, and here are some.
Yeah.
Yeah, great. Okay. Okay, it has image factorizations, or also called epi-mono factorizations. So if you think about sets, you can form all limits and co-limits, Brendan told us last time, and you can take any morphism from A to B, any function, and find a surjection and an injection that factor that thing. You can take the image of the map and factor your map as an image, as what's called image factorization, surjection followed by an injection. And that's true in any topos. So every morphism has images.
What is how do you interpret injection and surjection?
In an arbitrary category? Sure. There's lots of different ways. I don't know whether to say it the fastest way. So a map A to B is an injection, or actually it's called a monomorphism. I think mono means one, and that's like 1-to-1. I think is where they get the word mono from. Is a monomorphism if for all other objects X and pairs of maps into A, like I1 and I2 and F, if I1F equals I2F, then I1 equals I2. And surjection or epimorphism, epi meaning on to, is kind of things on the other side. So if you can imagine two different maps into here, and this was a monomorphism, and this thought that those two maps were the same, then they are the same. Okay. Okay, so the third thing is that it has internal HOMs. So one way to the fancy way to say it, and it's worth knowing the fancy way because that's how you search for it on the internet. Cartesian closed category. So our topos is Cartesian closed. Every topos is Cartesian closed, and you say it has internal HOMs. And what that means is that if you have two objects, then the HOMs from A to B, if I have two abelian groups, the set of morphisms from one to the other form an abelian group, so it has internal HOMs. I can take any two morphisms from one abelian group to another and add them, and there's a zero morphism. And abelian groups do not form a topos, but they have the category has internal HOMs. Every topos has internal HOMs. So in sets, there's a set of morphisms from A to B. There's a set of functions from A to B. And so to write this, so if we wanted to write the nice version of it, what we would say is for all, so this is what internal HOM is, a set. So for all A in our topos, the functor times A, blank times A, taking a set to a set, takes the set of naturals to the set of naturals times A, has a right adjoint. So we have set, and set, and we have times A, and then the backwards thing is called blank to the A, which is, so writing that out, I guess I'll write it here. The set of maps from X times A to Y is isomorphic to the set of maps from X to the set of functions from A to Y. That's what internal HOMs means, that this thing is the internal HOM. It's just shorthand for A to the Y. It has the right cardinality. The reason for it is if this has cardinality little a and this has cardinality little y, this would have cardinality little y to little a. Okay, so we have three properties so far: Cartesian closed, epimonofactorization, limits and colimits. Any topos has all those properties, so it's acting like sets are. Groups don't have this property. Groups are not Cartesian closed. Abelian groups are, I said. But lots of categories are, and lots of categories aren't, and toposes are. So the most interesting thing, and the thing that Brendan thought was the funniest remark in the book, is what we called a super dense nugget from outer space, which is the subobject classifier. So this thing is surprisingly powerful, and yet very cryptic to look at. It's like if we received this weird like satellite thing from outer space, and the scientists were just studying it for like decades. This is perhaps that thing. So what is it? It's an object in the category, and a monomorphism or a morphism 1 to omega that we're going to call true. Now you don't use a word like true in mathematics very lightly, since it's like you don't have very much namespace. You're not going to repeat different things being the thing that is called true. So this is acting as, that's our closest name for what this thing is. Yeah.
Think about your comment from point 3 that a Abelian group is Cartesian closed.
Mm-hmm.
Because wouldn't be adjoint tensor instead of the product?
Is adjoint. Oh shoot. Yeah. I guess is that right?
Or does that times have to be product, or can it just be?
That would be called monoidal closed. It's a good point. I'll have to think about it. So perhaps, right. So let's just say at least groups is not Cartesian closed, and maybe abelian groups is actually monoidal closed. That does sound right. Thanks. Okay, so this is an object omega and a morphism 1 to omega. And just a side note, in any category with a terminal object, a map from that terminal object to anything, to any other object, is monic. Whereas a monomorphism is an injection for all x. And the pullback, didn't give myself much room, the pullback of a monomorphism of a monic map is monic. So that's one thing I probably should have said in part 1. So what that means is if you have a monomorphism, A into B, and you have another morphism, so if this one's monic, and I write that with this symbol there, and this is anything, then I can take the pullback here, A times over BC. Then this will automatically be monic. That's true in any category. Okay, so I have a morphism from 1 to omega in a category. My category is a topos. It's a category. So I know it's a monomorphism. And so for any, if I have any map x to omega, then if I look at the subobject here, sorry, if I look at the pullback for all f, this thing is a monic map, because this is. So I have a morphism, I have a function from, for any map from x to omega, I get, by pulling back true, I get a subobject of x. A monomorphism into x is called a subobject of x. Or more technically, a monomorphism up to isomorphism.
So is that dot?
That dot is my name for x times sub omega 1. But that dot is just the pullback, whatever that is. Okay, so what I'm saying is for any x to omega here, I could pull back true and get some subobject of x. So given a map from x to omega, I get a subobject of x. That's true in any category. If you have pullbacks and you have a terminal object, you can make the statement. But what's true for a subobject classifier, what's different is that this is an iso. So I get to put an iso there. that's what makes it the subobject classifier, or a subobject classifier, yeah.
Is this like, so when we do the pullback development that we get, like the sub-object classifier, is that like a witness to the truth statement?
So I haven't unpacked this at all, so I'm going to do that now. What is this talking about? Somehow, in the category of sets, there's this object, this super important object, with a map called true from the one element set. So there's a set with this map called true, and we know that if I have any other thing mapping to this set, I can pull back and get some subset of the thing, some subset of x. And this guy is saying that for any subset, in fact, there's a map from x to omega. So what is that special thing? And it might not seem that exciting once you see it, because sets is not that exciting as a topos. But it is a topos, so we're going to get one. So does anyone know the answer? Okay, the answer is that the subobject classifier for sets is true-false. And what that means is for any map from x to omega, a map from x to omega is called a predicate. And what this is saying is that predicates and subobjects are the same, or are in isomorphism. Predicates on x are the same as subobjects of x. What's a predicate in grammar or in English? You have a sentence as a subject and a predicate. Bob ate the candy. Okay, so ate the candy is a map from Bob behavior to the subobject classifier. For any Bob behavior, you get true-false. So what subobject of that? It's all the Bob behaviors where he eats the candy. So we're trying to do that again. So here we're saying that a map from x to true-false. Well, I can look at the subset true. The one element set maps into here by picking out true. And I can take the pullback. So if I have some map from x to true-false, I can take the pullback of true, and that's the set of x and x, such that f of x as an element of Booleans is true. And that's always a subobject. That's a pullback. And what it's saying is that for any subobject of x, to go, okay, what this isomorphism is saying is that for any subobject of x, there's a predicate on x that cuts it out. So let's give why don't I'll let you guys work an example. What is the predicate on n such that that cuts out I guess, sorry, let me just say some terminology. We could say, given a map from x to omega, we could say it cuts out a subobject of x. And given a subobject of x, we could say it's classified by a predicate. And these are an isomorphism. Okay. So what is the predicate on the natural numbers that cuts out a certain subobject, namely the evens? And what is the predicate that cuts out the numbers less than 10? Okay, so I'll just give you 2 minutes to think about what am I even asking here. It has something to do with this scroll over there. What am I even asking, and what is the answer to that question? Okay, go ahead. Or do you need some help? Do you need some,
So
yeah.
is n like
N is the set of natural numbers.
and how is that represented in set?
It's an X. So the subobject classifier is a certain set, namely true-false, such anamorphism from 1 to omega, namely the one that picks out true, such that for any set X, the set of maps from X to omega is in bijection with the set of subobjects of X, the power set of X. And so now here's a set, the natural numbers, and here's a subset, and here's a subset. So what predicates cut them out? That's the question.
What is predicate?
A predicate is a function from X to true-false. So it's kind of like the predicate is even, is less than 10. That's an English statement that a predicate could say. Is less than 10 is a map from naturals to true false. Yeah. I'm not saying this is hard. If you're looking at this like, wait, is this hard? It's not. It's just a matter of do you have the definitions in mind well enough to answer the question.
That's what it is. Yeah, that's and then also that's the separation. Well, okay, yeah, that's what it is.
Okay, any answers?
So basically it's just this, right? Separate all of the parts. All the functions. All the
So the first thing to understand is what am I even asking? And what I'm asking is, here's a subset of n, so it's sitting there on subset of n. And I'm supposed to turn that somehow into a map from n to true false. And by map, I mean a function. Such that when I take the pullback of true, I get this set. Something isomorphic to that. So what is question mark? It's a function. Is even. Well, what does that mean? So what does it say? Where does it send n?
To n mod 2 interpreted as, or sorry, mod 2 plus 1 interpreted as
Sure,
true
yes.
or false.
Okay, so it sends it to true if n is even, and false if n is odd.
What is that morphism true there? Is that a constant morphism? Or
It's a function from 1 to here.
that's always true?
It's always true.
Okay. Oh, yeah, morphism.
Other questions? Yeah.
There are definitions for sub of x. I understand what it is in set, but
Yeah, it's this. So it's you take all monomorphisms into X, but there's a category of those. So I have a monomorphism, I have another monomorphism. I could have a map between them, but I don't want a category. I just want a set of all subobjects of X. So I take all isomorphism classes. So what that means is this is actually slightly different than the set of n in n, such that this weird F map, F of n, equals true. I mean, actually, no, I guess they're exactly the same set. But I guess I could say, maybe I'll do it this way. So it's the set of n in Z such that negative n is greater than 0 and even. I mean, some weird, stupid way of writing the same set. It's not exactly the same set, but these are isomorphic sets. They're isomorphic sets if you take any number and ask it to be negative and or non-positive and even, then I can send it to its negation and go here in this commute. And so what a subobject is it's a monomorphism or a class of monomorphisms where we consider two equal if they're isomorphic.
and that is always going to be an object of whatever category you're working in.
Ah, right. Right, this is external, I guess. So this is the case. This is the set of maps from X to omega is in bijection with the set of subobjects of X.
Which happens to be internal to set, but is not
Right.
actually internal to the category that you're topos that you're working
Right. Internal to the topos you're working with, this thing is the right thing. Like the Hom object from X to omega is the right thing. Yeah.
Going off on that, what does ISO mean if these are not internal objects? Like, do you just want the bijection between
Bijection,
sets?
yeah.
Or is there like a naturality condition?
This is a bijection between sets. Yeah, no naturality required. Other questions?
If subobject is just defined in terms of like monomorphism, like since like the integers have the same cardinality as the natural numbers, wouldn't then like the integers be a subobject of the natural numbers
If you give me a monomorphism from the integers to the naturals, you've given me a subobject.
Okay.
The isomorphism has to respect the inclusion.
The isomorphism has to respect the inclusion. So if I have two different subobjects of the naturals, but a map between them that commutes, and then I consider them the same subobject.
So
We did this for partitions on the first day. We said it's a map, it's a surjection, but if I had another thing that it was surjecting to, and there was an isomorphism between them, then I would consider it the same partition.
So a subobject is not like an object of X. It's
A subobject is
isomorphism class of monomorphisms.
A subobject of X, I mean, that's like saying, is the set of evens a subobject, is it an object of the naturals? I think you said it like that. It's not an object of X because X is a type like the naturals. It's a subobject of that type.
So it's not an object of set either. It's
A
an
subobject?
equivalence class of objects. Well, it's,
Yeah. In the
of
category
inclusions, right?
So let's say we're in graphs. Okay, let's do this whole thing again in graphs. We have limits and colimits in graphs. We have epimono-factors that you can take the image of a graph map. Graphs are Cartesian closed. There's an X, given two graphs, there's a graph of maps between them. What are the vertices? If I have a graph G and H, the vertices of the graph of maps from G to H, there's a graph of maps from G to H, and its vertices are all the maps from G to H. Sorry, these are reflexive graphs. Let's say I'm saying reflexive graphs. The vertices are all maps from G to H, and the edges are given two maps from G to H. If there's an edge between every vertex and we're in one and the other, then I'll put an edge between them. Those are the edges in the graph of maps. So all the things I'm saying work for graphs. And finally, there's a certain graph called omega the graph. And omega the graph has a map from the single vertex graph into it. And such that for any other graph, and any subobject of that graph, so subgraph, there is a map from the graph to omega that cuts it out. I don't know what your question was anymore because I talked for a long time. but all of this stuff works in any topos. And in any topos, we're going to look at the subgraphs or the sub-database instances or the sub-whatevers. Here, we're going to look at the set of all maps from that instance or from that graph to this special graph.
Right. So I guess what I was asking was, intuitively, a subobject of a set is a subset.
Subset.
But the way you would formally define it is as an equivalence class of monomorphisms
Yes.
into the object.
Yes.
Okay. So
Because
it's
in
not
set
actually an
theory,
object.
sets are very special things where like I could have a set with only one element, but that element was like the naturals that are twin primes. That's like a one element set. One element is twin primes. But that's kind of, from category theoretic point of view, that one object is just a dot. It doesn't, that one element is just a dot. It doesn't mean anything. So instead of having subsets where like I retain their meaning somehow, I just have some dots and not others. And I can't tell where I got these dots. So if I have some dots, if you give me some subset of dots and someone else does also, as long as they're the same, like, yeah, I don't know how to say it right.
But what's
Yeah.
misleading about the terminology is that it's not just the object, it's not just the set, it's the inclusion into the
set.
other
Yeah,
thing.
it's the inclusion into the set. Yeah.
So a sub-object is not, in any real sense, an object of the topos.
Right. A
Like it's an
subobject of
equivalence
X
class
is
of
not really
morphisms.
an object of the topos. It's a monomorphism of the topos, or it's a class of monomorphisms. Yeah.
Just a matter of interest, what is the omega for graphs?
It's a pretty weird one. It looks like this for some reason. I mean, you just figure out what it has to be, and for some reason it looks like this. I mean, I can tell you the reason, but you'll have to stay after class. Okay. Other questions? The subobject classifier for graphs. Okay, other questions? Okay. So now I'll tell you about lots. So all this stuff that I've been saying works in any topos. And from what we have here, this little nugget of whatever this is doing, kind of like a junction, when you first see it, it's like, what? Why is that so important to you guys? In the same way, why is omega so important? And the reason is because it allows you to do logic. Just like true-false allows you to do logic. Where would you start with logic without true-false? In temporal type theory, where these behaviors on that board live, the logic is not true-false, but when. It's not like always true or always false, but like a logic of when is it true? When was the controller acting up, or when was it acting right? So for example, I have this map called true from 1 to omega in any topos, but that gives me a map from 1 to omega times omega called true comma true. And that's a subobject, because any map out of 1 is a monomorphism. So if I ask, I know that for any monomorphism, like true true, there is a certain thing that classifies it. There's a map from omega times omega to omega classifying that subobject of omega times omega. Classifying means that this will be a pullback. And so I get a map in sets, for example, from true false times true false to true false. What map is it?
Or?
Yeah, is it and, is it or?
XOR?
XOR? Well, you're right that any binary operation from true false times true false to true false classifies some subobject of true false times true false. And this one, we know that this has to be the set of all elements AB, I guess, or Boolean 1, Boolean 2, in omega times omega, such that f of B1, B2 equals true. Okay? That's supposed to help somehow. The answer is, if this is the set true, true, then f has to be, as someone said, and. One is the set of all, like this map here is probably, you could probably write it as like true, comma, true. The one element set consisting of the pair true, true. Yeah.
But it could be like in the top left corner, we don't have any like subset.
Any subset, I need this to be a pullback.
But
So that-
but can it be like true, false, false, true, false, false?
Yeah, let's try. Okay, let's say, so what this is saying is that true, true is classified by and. Like, I have two, if I had some x, and I had a map to omega times omega, it'd be like I gave myself two truth values for every element of x. And if I want that when I go across this thing, that they're both, like, that I get to true, that would be saying that both of those things are true. It's like the two things I get are true and true. If the two things I get are true and true, I can say that the and of them, so if I call this P comma Q, then this would be called and of PQ, or P and Q. Because the only subset of things that do that are those that go to true comma true. Probably nicer ways to say this, but that's what it is. So we could take any subset of omega times omega and get a map from there to there. So for example, you could say omega times 1, times 1, mapping to omega times omega by identity on the first part and true on the second part. What would this be classifying? This is taking two truth values, P and Q, and asking that I don't care what the first one's doing, but the second one has to be true. So this is basically just asking, what is P? It just projects onto the first coordinate. But the reason I set this up is, now I'll do omega times omega, with omega times 1, plus, or coproduct, 1 times omega. There's a map that on the first factor first factor is omega times true, and on the second factor is true times omega. And that classifies, any guesses?
That's all.
That classifies, this is plus, so it's saying, I am happy with a certain pair of truth values. Happy means goes to true. If either you're in this side or you're in this side, either you're anything and true, or you're true and anything. So this is just actually standard or V. So I'm trying to write these in ways that would work for any topos. In the category of sets, it's much easier. I would just I'd write something like true, false, true, false, comma, true, true, comma, false, true. That's a set. That maps into omega times omega, which is true, false times true, false. And this is the classifier. This is classified by or. And this is a much more concrete way of looking at this kind of thing. This is saying anything comma true or true comma anything. So this is a more abstract way you can write it that's true, and it works in any topos. Any questions? Are you following roughly? People following? Yeah.
So are you drawing these diagrams like they seem to be just showing that you have subsets of omega cross omega?
I have various subsets of omega cross omega that I think are important ones because they classify operations, binary operations from omega times omega to omega, that I think we all agree are important, like and or. Yeah.
To clarify the bottom example, the left vertical arrow is not monic.
Right.
Oh, you're right. You're right. I'm supposed to take this. Okay, I'm supposed to sub-factor this. Good point. Sorry. I'm supposed to factor this using epi-mono factorization or image factorization and take its image in here. And that's the thing I meant to say was, great point, thanks. That's the pullback. Yeah. Okay. So how would you get empty set? Sorry. How would you get false in any topos? So false is an element of omega. So how would we get false? What subset of 1 should we use to get false?
The empty subset?
Yeah, the empty subset, which is always the initial, it'll be the initial object of our category, but it's actually, we could figure this out directly because it has to be the pullback of this diagram. So I take the set of things in 1, comma 1, such that false equals true, which is the empty set. And so on. You can get implication. You can get. You can actually get for all and exists in any topos. You can write what for all means and what exists means, where you start looking at omega to the x, and you ask for maps from omega to the x to omega. It takes a state. What is this thing? This is the graph or the set or the element of the object of the topos, the class that is all about all maps from x to omega, which are all predicates on omega. Remember, a map from x to omega is a predicate. So for any predicate on omega, we could ask for all to be true. We could ask, is it true of that predicate that no matter what x I plug in, it's true? And there is a classifier for that, and another one's for exists, etc. And so what that allows you to do is in any topos, take any logical statement you've seen, like the definition of real numbers or something, and write that out using logic. And that logic compiles into some meaning in the topos. Yeah?
Would it be a stretch intuitively to say, with regard to the lower right-hand corner on the middle board, that in a way, set x omega is sort of a static categorical analogy to a trained neural network? I mean, in a certain...
Okay, so the network is, output is a 0, 1, or a...
I mean, it's a functional... It has certain flavor...
Yeah, a trained neural network at the end of the day is just a function from inputs to outputs. And this is just a function from inputs to outputs. So I suppose so. But it didn't do any learning, so it's,
No.
I always find the idea of trained neural networks kind of weird because they're just functions that someone got somehow. But yeah, yep. And, right, okay, so if I had a trained neural network, then I could classify, then it classifies sub-objects, namely those, like if a neural network knows how to understand whether an orange is ripe or not, then I'm taking the subset of oranges that are ripe. Other questions? Okay, well, let's stop here. And oh, by the way, there's a talk this afternoon if you're interested in the seminar in about an hour and a half on game theory. Jules will be giving it. And then, yeah, or stick around now for more fun with toposes. Oh, in 2.